close this. So briefly about myself, I am a metallurgical engineer. In this discussion, or in the presentation, I used the term materials engineer, but metallurgical engineers fall into that. So my focus is on metals. So I have a bachelor's and master's in metallurgical engineering and a PhD in material science and engineering, with the focus on metallurgy. And I've been working for over 30 years helping companies with engineering the metals that are used in their products. This includes helping with selecting materials for products, for product design, developing manufacturing processes, helping with quality improvement, and then working on failure analysis and root cause analysis to solve product failures or quality problems. In addition to the engineering, I also offer training. This includes on-demand courses that are on the website, present webinars like this, and also on-site training and company training. And if you'd like to reach me afterwards, my phone number and email are here on the slides. So I'm going to start off with this discussion about products in general. So to me, to materials engineer, we see products as being essentially a collection of materials. These materials have been shaped and modified to make the different components, and then those components are brought together to make the product. And so during product design and also the other stages of product design and manufacturing, what we're doing is we're engineering the shape or the form of components and engineering the materials, and the goal is to create individual components that have the performance and reliability needed for the application. We also want to design components that are easy to fabricate. That helps to keep costs low. We want to design components that are easy to join together. So if they're going to be welded or soldered or brazed together, we want to make sure that we select the materials in the form that enable easy assembly by these different metallurgical processes, because easy assembly results in reduced cost. So take a step back. This is Clearly, this presentation will be about materials engineering and how we can reduce product cost through materials engineering. So this will sound like an unabashed promotion of materials engineering, and well, it is. What I've seen is that there are many aspects of product design and manufacturing that involve engineering of the materials used in the products. And these decisions and also problems can benefit from materials engineering expertise. They need someone who understands different materials, their properties, the different tools that are used to analyze materials, and then how to use the information from analysis to understand what's going on with the materials for supplier evaluation, or to select materials, or to fix a problem. But a problem is that engineers from other disciplines are the ones making many decisions and solving problems that involve materials. Now, in my experience in working with these engineers, the vast majority are skilled engineers, but they have little or no training in materials science and engineering, and their expertise is not on materials properties and evaluation and characterization and processing. So decisions are sometimes decisions are made where using material that might be suboptimum, either for cost or reliability or performance, or problems linger around because people don't know what to do to get the information needed to solve the problems. So I'm going to be talking about how materials engineering can be used to contribute to reducing the costs of products, and in many cases this is also helping to prevent problems that result in higher costs than necessary. So the cost to produce a product is related to three things, basically, if we're talking about just direct costs. And that is the components that are used in the product. These are the materials in the components, the fabrication methods that are used to make the components, and whether it's machining or casting or extruding, and also ease of fabrication. When it's easy to fabricate components, then the costs are lower, and when it's difficult to fabricate components, then the costs are higher. There's also the assembly, the processes that are used to to the processes that are used to assemble parts together, whether it's welding or soldering or brazing, and also ease of assembly. And finally, there's quality problems. This can be both problems with supplier quality or internal production quality. In either case, when quality problems come up, then there's scrap and rework and other things going on that cost money. And so there are things that can be done to either prevent the problems from occurring or to quickly solve the problems so that the costs associated with quality problems are as low as possible. So for reducing component costs, there are a number of different things that can be done. The first is to identify lower cost materials that meet the design requirements. So the first thing that needs to be done is to understand what are the different design requirements, what are the performance and reliability requirements, how will the components be fabricated, how will they be joined together, are there weight requirements or size and shape requirements. So quite often there are lower cost materials that are available to meet the requirements. In many cases, people for a particular design, for a particular product, people are comfortable with certain materials, or certain materials have been used in past products, and people want to continue using those materials, even though other materials might be available that provide the performance and reliability at lower cost. So it could be and some things may be like eliminating secondary processing. Also, do the materials that are being used provide more performance and reliability than needed, and are there lower cost materials that still provide the reliability and performance needed, but not as high as the materials that are currently being used? So the materials, you're paying more for the materials that provide more performance and reliability than necessary, and maybe a lower cost material is available that still meets the requirements. And finally, maybe using coatings as a way to use a lower cost material but still give the properties that using a higher cost material is currently providing. Then there's also using a different fabrication method. So some fabrication methods are more expensive than others to use, whether you're using machining or extruding or forging. And perhaps it's possible to, rather than machining a component, to cast the component, having a near net shape component that might just need a little bit of machining after casting. And so that would also require using a different material, but we can select a material that still enables meeting the performance and reliability requirements. So we can machining bar versus casting, trying to eliminate secondary processes where possible. So maybe eliminating a heat treatment, or applying a coating, or eliminating extra machining after the part has been fabricated. And the final thing is ease of fabrication, and this is a big thing. Ease of fabrication refers to how easy it is to fabricate a component into the shape that's desired from the materials that have been specified. So if you're having if the part is being made by a supplier, then you're concerned about the cost per part, the cost per piece. And if it's an internal, if you're fabricating a part internally, you're concerned about the cost of scrap, rework, extra inspection, extra whip, basically any hassles associated with fabricating the part. In terms of having a part fabricated externally, some of you may be familiar with sending a drawing out to a supplier and having them provide a quote that you might think is higher than expected, or they might even no quote a part. The reason for the high cost or the no quote is that the supplier recognizes that the part is going to be a hassle to fabricate, and they don't want to they don't want to deal with it, or they're going to charge you for it. And so designing for ease of fabrication is important for keeping suppliers' costs low, or to be able to get the suppliers you want. So ease of fabrication is related to the materials that are being used, and also the shape and the form of the component. Some materials are easier to work with than other materials, and for different processes, some shapes are easier to obtain than others. So for example, with die casting, the part has to have a certain draft to it so that the part is easy to remove from a mold. But if the part isn't designed properly, then it will be a hassle to remove from the mold, and the supplier will charge you for that. Ease of fabrication also affects internal fabrication in terms of scrap rework and extra inspection. So design for manufacturing is important. When we're thinking about design for manufacturing, we're selecting the form and materials that improve the ease of manufacturing, and also I'll discuss in the part on assembly, ease of assembly. And this is done during product design. So for example, if you're going to machine a component out of steel, you can possibly use an alloy that contains lead, and that will enable easier machining and faster machining. If you're going to be want to make 5,000 parts a week, that might be a way to go, because having lead in the steel enables faster machining. If you want to have a heat-treated part, a steel part, then selecting a steel that has good hardenability will enable using a heat treatment that does not result in cracking or distortion of the component during the heat treatment. And any cracking or distortion can be a problem in terms of scrap or having to babysit the part and taking extra steps to monitor the part or monitor the process to prevent the problems from occurring. For reducing assembly costs, it's the same thing. It's thinking about design for assembly, thinking about the component form and the materials that are being selected, and the joint that's being selected, whether it's a solder joint or a weld joint or a braze joint, and whether it's a butt joint or a lap joint. And designing selecting the materials and the shape of the components and the type of joint so that the parts are easy to join together. Also, the assembly process that's being used is also important, and the cost of the process impacts that. So perhaps using a lower cost process will result in lower costs to make the product. And the final thing for reducing product costs is reducing costs of poor quality. Cost of poor quality come into scrap, so throwing away parts that you fabricated or product that you've produced, rework, extra inspection, and add an extra WIP that has to be built up because you know that there's going to be problems at some point in the process, and you have to have enough material in the line so that downstream processes can continue on. This is all a lot of cost and a lot of hassle. The first way to reduce the cost of poor qualities is to prevent the problems from occurring to begin with. So from the materials engineering perspective, we want to select materials that enable easy fabrication and assembly. We want to write thorough material specifications for the materials that are used in components so that suppliers understand what's required of them, and that also your manufacturing line understands what evaluations need to be performed to evaluate the materials. Also, we want to go through a thorough supplier evaluation process to make sure that those low-cost suppliers that are way overseas are truly capable of providing materials or components that meet your requirements, that have the properties that are needed for the application, and that where manufacturing defects are kept below some maximum amount, so that the defects don't cause a problem in your product. A lot of times supplier evaluation doesn't involve materials engineers, and so suppliers are able to provide materials, or people select suppliers that don't have really the capabilities or the knowledge and the expertise to provide the materials or the components that you need. And with internal production, the way to prevent problems is to develop capable manufacturing processes where the inputs are well characterized, understand the materials that are needed, understand the process parameters, and understand the effects of the process on the materials that are being processed, so that the materials at the end have the desired properties and that the level of defects is below whatever the maximum amount that you need for your product to have the quality needed. So a lot can be done to prevent problems, but problems will still occur. When problems occur, we want to fix problems faster. Whether it's a supplier problem or a problem with your own manufacturing line. And we have to perform a root cause analysis, and the first step is always going to be performing a failure analysis. We want to evaluate the materials to understand what's going on with the materials. The beauty about performing a failure analysis and analyzing the materials is the materials don't lie. It's just we have to ask them the right questions, but if we ask them the right questions and perform the right analyses, it will give us information. The analysis will provide information that will help us understand, is it a problem with the input material, is there a problem with the manufacturing process, what's going on with the manufacturing process, or maybe it's not maybe the problem is that the material is okay, it meets the specifications, but the material really isn't appropriate for the process, and we can have to modify the specification and use a different material. For an example, I worked on a project where people were taking tubing and bending it and to form components, and sometimes the tubing was fracturing or was splitting at the welds, and it was determined that the specification for the carbon content of the tubing was too wide, so that the specification had to be narrowed to have a lower carbon content. So we still we're able to continue to use carbon tubing. It just was a lower range of carbon was allowed for the application, and that was okay, and that ended up resulting in a huge reduction in scrap and an extra WIP in the process. So failure analysis is always the first step. We need to get the information to understand what's going on with the metals, and then from there figure out the root cause of the problem. So this involves failure analysis involves collecting the samples and background information, evaluating the metals using the different tools that are shown here, like using looking at the microstructure using a microscope, looking at fracture surfaces or crack surfaces using a scanning electron microscope, evaluating the chemistry of the material, or evaluating its mechanical properties like its tensile properties or its hardness. Then we want to review the data and understand what the data is telling us, and what it's telling us about the materials and what's happening with the materials. From this, we can identify the metallurgical reason from the problem, and from that we can identify or narrow down what the root cause of the problem is, whether it's a design issue, a supplier manufacturing issue, a process issue, and so on. And that helps get to the problems very quickly, and you can typically resolve problems in a matter of a few weeks once we get the information from a failure analysis. So in this presentation, I explained how materials engineering can have a big impact on product design, and on costs related to materials used in products, both from the design perspective as well as solving problems. And so the takeaways is that in many cases there's a missing piece from engineering teams, and that is metallurgy and materials engineering expertise. This never ceases to amaze me. I think that people, unfortunately, there's so much information on the internet, people think they can get the information they need from the internet, and sometimes this information is helpful, but a lot of times it's not helpful, and people end up making decisions based on this information, and they don't get anywhere. What's really important is to have metallurgy and materials engineering expertise available to you, and there are a lot of people available that can help out. And also, interestingly enough, in some companies, they have materials engineers and metallurgists on staff, but people in the organization don't know to go to those people to get help during product design or during manufacturing process development or during supplier evaluation or when problems arise. It's kind of weird. We can reduce the costs of products by engineering the materials and components to come up with, use lower cost materials, and to design for manufacturing to come up with parts that are easier to fabricate and easier to assemble together. And we can apply metallurgy and materials engineering to quickly fix quality problems. So that is it. There is a brief survey that will open up after you're done. It'd be a huge help if you just took a minute to complete it. There's only a few questions. My contact information is here. You'll also get an email with a link to a special discount off of our Principles of Metallurgy course if you're interested in starting to learn how metals can be engineered. And finally, if you have a problem, please reach out to me. So